Hello all, welcome to the subject VLSI Design and Technology. I am Professor Meenakshi Pancha from Electronics and Telecommunication Department, Parvatibai, Ganma, Mojo College of Engineering, Waguli. So today we are going to discuss about metastability and its solution. First we will see from the introduction part, what is the metastability? Metastability is a type of failure which occurs when digital circuits attempts to synchronize asynchronous digital data. Here the shown in figure when a clocked flip-flop synchronize an asynchronous input, there is a small probability that the output exhibits an an unpredictable response. This phenomenon occurs when the input transition changes setup and hold the time specification. This occurs within the small timing window where the flip-flop accepts the inputs. Thus, under this kind of circumstance, the flip-flop enters in an unstable intermediate state, which is as called metastable state. In this case, a slight deviation leads to the output to revert to one of the two stable states. However, the settling time depends not only on the gain bandwidth products of the circuit but also on the original balance and the noise level of the circuits. Here, showing in a figure second, a critical triggered window. The name is TW is defined if the flip-flop timing constant is changed during the time window TW, the output Q is still unresolved within a decision time TD. Here, referenced to the beginning of the trigger event, which is the positive clock edge for the sample circuit, as shown in a figure B. TD thus includes the normal propagation delay TCO and extra delay due to metastability TM. The relationship between TW is equal to FTD is used for defining the metastable behavior of the flip-flops, and the exponential function is asymptotic, valid for the relation as shown below. TW is equal to FTD is equal to A star exponent of B into TD. The probability density function for actual setup time is unity for one clock period. The probability of one data event to hit the critical window TW is equivalent to indicated area TW bar TCLK. With given TW, the reliability mean time between the failure of the synchronizer is calculated here shown in a figure that's equal to 1 by 4th of TW TD into F clock into F data. This is about the metastability. What are the measurement setup and the parameter? We will see in the next slide. Here, the figure shows in a slide is a test circuit to measure the metastable parameter of a synchronizer. Here, in this case, we use two different pulse generator to provide a data rate of 1 megahertz and a clock rate of 2 megahertz. The data transmissions are randomly and evenly distributed over the entire the clock period of the about one transition per clock cycle. The data transitions are also evenly distributed within the failure time window TW. At the output of DUT, there are two well characterized sampling flip-flops, and these two flip-flops use the same clock signal used by the DUT. The first sampling clock is delayed by AD since the probability decreases exponentially with the time and the condition easily satisfied, and to run the test TCO is used as the base delay with the TW is equal to T. Here the different MTBF with increasing Tm until MTBF is greater than the 60-second is taken. When the MTBF results are plotted on the Samilog paper, they give series they give rise to best fit straight line with the slope 1 by 2k to k1 and is calculated by intersecting a k2 value into kmpf. Now we have got the equation. Further we will see k1 and k2 will easily find the TMOS chosen MTBF clock and frequency data. Let's see one by one what is asynchronous circuit improves. Here we will see how to improve the synchronizer circuit. Although the circuits show extremely quick metastable settling time, the designer has to still improve the MTBF by using its unique internal feedback configuration. Here the figure shows the gated latch, which is internally latched as the asynchronous input on the falling edge of the system clock, and the generates the signal Q1. The input for the Q1 through the internal feedback path eliminate a possible hazard conditions during the clock's high to low transition. Thus, the latch holds Q1 stable to assure the setup time requirement of the subsequent flip-flop and accept data on the next rising system clock edge, similar to stage synchronizer, when the probability that the data goes metastable is a multiplication of two possibilities of each synchronizer. Therefore, since the probability of failure becomes small when MTBF of the digital device improves. While using the measurement setup above, the designer get K1 is equal to 3 into 1046 and K2 is equal to 0.05 nanosecond with a gated latch. Let's see how to design the finite state machine. Here, the second figure, this shows the design of finite state machine. For a sequence logic system, the number of output, that is n naught, depend upon the present and past. The value of the input. Sequential logic systems are known as the finite state machines. Finite state machines are considered to have number of the internal states which are determined by some combinations of the value of n s state variables, and which is also changes to a new state depending upon the present state and the input. The output depend upon the present state and the input, or just a present state. There are two types of finite state machine. First one is synchronous state machine and asynchronous state machine. Let's see one by one. So first see the synchronous finite state machine. Here shown in this diagram. This diagram shows the synchronous finite state machine. Operation of a synchronous, which operation of the synchronous finite state machine is carried out by using a clock. At each clock event, the state changes to new state, which is determined by the present state and the input. But in the asynchronous finite state machine, here the system do not have the clock and the internal state changes depending upon the change in the inputs. Asynchronous finite state machines are mainly used where the fast response to input changes, and which is also used where the introduction of extra frequency component related to the clock should be avoided. These are about the finite state machine with the synchronous and asynchronous configuration. Let's see some of the difference. The synchronous finite state machine's operation is carried out by external clock, whereas the asynchronous finite state machine operation is carried out by input variable events. The D-type flip-flop are used to store the state variables, and gate delay are used to store the state variables. State variables are changed at the same time, but in asynchronous, state variables are not changed simultaneously. The FSM is a type of the sequential circuit which is designed to sequence through the finite state in the predefined sequence manner, and which is consist three parts. First one is sequential current state register, combinational next state logic, and combinational output logic. So what is the sequential current state register? So in this, the register set of n bit flip-flop are used and are clocked by clock signal to hold the state vector of the FSM. For the state vector of n bit to n possible binary patterns are used for state encoding. But in the combinational next state logic, as we know that the FSM stays in a single state, and at each active transition changes from the current state to next state. The next state is always a function of the input and its current state. The combinational output logic, here the output in the Finite state machine seems to be a function of the current state and the primary input. Generally, in the more finite state machine, the user want to derive the outputs from the next step. Let's see the state machine diagram. Here the figure shows all basic elements that make up a state machine diagram. First, see what is the states. States is a determines machine's outputs. Every state machine has at least two different states along with the transitions. States are fundamental components of each state diagram, so which will be represented in a circle. Default state. The designer declares a state to be default state. The machine transits to the default state if no transition from a given state takes place. The default state is useful for the debugging state diagram. Next one is trap state. Here the designer declares a state to be the trap state. The machine transitions to the trap state on the nearest active clock edge. Further, the machine can be in a state different than S1, S2, S3 since the register 0 signal acquires only three values S1, S2, S3. Furthermore, if synchronized code tried to simulate the synthesized net list, minimum 2 bits are required to encode all the machine states. For a machine encoded using a 2-bit status word, we got one additional unused state. A transition is change of the current machine state from one state to another, occurring on the active clock edge. If it evaluate to true, the transition associated with this condition take the effect. Next is transition priorities. If two or more transitions coming out of the same state when you simultaneously evaluate to true, they should have different transition priorities assigned. By default, all the transitions on a state diagram have priority 0, which is the highest possible. Priority value can range from 0 to 9. A transition with a lower priority value takes precedence over the transition with a higher priority value. The action is set of hardware description language statements which assigns new value to port, internal signal, and the variable. The statements that occurs in the actions are signal assignment and variable assignment. So there are two basic kinds of the action, state action and transition action. State action is defined for the state and which is performed when the machine transition to specific state. The behavior of combinational and the register signals port involved in a state action is the same. The HDL statement defined in the state action are executed on the active clock edge. The state action can be used to model the Morris machines. Similarly, the transition action here, what will happen? It performed when the machine performs a specific transition from the specific state. The behavior of the signals or ports involved in transition action differs from the combinational and registered type. The assignment to the combinational port signals are executed asynchronously with the changes of inputs to which the transition is sensitive. Assignments to registered the ports or signal are executed only on the active clock edge. The transition action can be used to model the Millis machines. The two next actions type are designed to reduce the number of the transition action shows in a figure. Entry actions and exit actions. So what are the entry and exit action is nothing but entry action is defined for the state. It is transition action that is the performed on each transition to the an exit action is defined for the state. It is the transition action that is the performed on each transition from this state. The combinational and the registered signal updated in a state actions. How differently combinational signals are sensitive or synchronously to the machine outputs because they are updated by the concurrent signal assignment. The registered signals are updated within the machine process so they can change only on the active clock edge. Encoding state and transition actions with the variable assignments as the variables are declared in the process statements. Variables assignments may occur only within the process. The location of the action assignments to the variable to the same as that of the action assignments to registered signals. See the variables and internal signal of the details as shown in a figure. So next the reset. The machine transitions to be state defined as the machine's reset state if the reset condition is true. The transition to the rest state is asynchronous or synchronous. The machine with the asynchronous reset transition to the rest state when the reset condition becomes. Let's see one example of the state machine. The example of simple state machine is a JK flip-flop. A JK flip-flop is a sequential device with a two inputs and two outputs and one clock input. Here the figure shows the JK flip-flop which is having two input, two output and one clock input. JK flip-flop output changes on negative edge of the clock signal. The NQ output is the inverted Q output. The Q output turn 1 when J equal to 1 and K equal to 0, and Q output will be 0 when J is 0 and K is 1. The Q output turns the positive value when both J equal to 1 and K equal to 1, and Q output remains unchanged when both J equal to 0 and K equal to 0. The above description of the sufficient to create a state diagram. Here there are a two state S1 and S2. So when j equal to 0, the state will be remains 0. Consider the q equal to 0. When the j is equal to 0, the state will be unchanged. When j equal to 1, it will state changes from 0 to 1 to next state j equal to 1. Then if j is 1, so it will remains unchanged. When j equal to 0, it will again change the state from S2 to S1. These are the state diagram of JK flip-flop. The state diagram includes all basic diagram items which are states, transition, conditions and actions. Let's see more a finite state machine. Here the figure shows the more a finite state machine, which is a sequential network. The output is a function of only a present state. In more a finite state machine, the output is associated with the state here shown in a figure. Here shown this in this figure. The output is shown inside the state. Since the output is same as the state machine is in that state, the combination is shown by an internal state. So the more a finite state machine is a faster, the output can arbitrarily complex but must be same every time the machine enter that state. More a machine realization is more complex than the delay due to the additional state requirement to derive the required output. The output of Moore machines are generally robust and independent of external inputs. Similarly, here the third figure shows the truth table of finite state machine. Let's see Millet finite state machine.